feel free to ask those. But I'll get started nonetheless. So just a bit of background. So when we talk about pipe network modeling in TwoFlow, really we're talking about a numerical software engine called Esri, which is the 1D component of TwoFlow. So when you purchase TwoFlow, you get Esri embedded within that automatically. And it's a very powerful engine that you get. Like most 1D solvers, it solves the full 1D Sanford-Nant equations. It's an explicit finite difference method, and it was first developed in 1972. So it's got over 50 years of heritage. And probably for about 30 years of those 50 years, it was primarily used as an internal tool. But certainly the last 23 years, it's been used as an external commercial software that people have been able to utilize. And it has capabilities in being able to model open channels, culverts, and subsurface pipe networks, and all the structures that you would associate with both open channels and subsurface drainage networks. So bridges, weirs, sluice gates, and also the operation of those. In terms of the 1D modeling and the schematization, like most 1D modeling software, it's made up of a series of nodes and a series of links. It's the nodes that store the water. So that's what's solving the mass balance part of the equation. And then it's the channels or the links. These are what are solving the momentum equation. So how flow, discharge, and likewise velocity transfer between adjacent nodes. So just a bit of background as to what we're talking about here when we talk about subsurface drainage networks. It's a series of nodes and links, channels for conveying the water, the nodes are storing the water. So we'll now focus on urban drainage. A little bit on the terminology. It's a little bit confusing when you start reading the manual, the TwoFlow manual, and I think this is because it's developed or was written by the guys in Australia who have very specific bits of terminology. And it certainly took me a lot of time to get my head around because we use slightly different terminology in the UK. And obviously coming from an InfraWorks background, I'm used to concepts such as conduits and manholes, whereas the idea of nodes and pits is slightly different. So firstly, we have the pipes. These are represented within a 1D network line layer. As I've said, I'm not going to go over too much detail in terms of pipes during the rest of this session, primarily because they're quite self-explanatory. You have a link between two nodes, you specify a shape, you specify some dimensions, and then you can specify an an upstream and downstream invert levels. We then have the nodes, which are the water level calculation points. Now, these can be specified using a 1D network point layer, but they can also be automatically generated at the ends of the pipes. We can then also have manholes. So these are sealed access points, and this is where TwoFlow generates the hydraulic losses. So energy losses to do with the manholes, the turbulence as flow goes into and out of those manholes. Again, TwoFlow can automatically generate those based on your pipes, but it is possible to override that, and we'll talk about that a bit later on. We then have this concept of pits, which is a very Australian term. We don't use it in the UK. We would probably call them gully or inlets. And these are sort of entry and exit points into the subsurface network from the 2D surface. So they allow that bi-directional coupling of flow from the surface to the subsurface. Now we add these as points, but in reality they are zero length connections. So we add them as points, but what we're essentially representing is a zero length connection from the surface to the subsurface. There's various different ways of representing the flows or the transfer flow, and I'll talk about those a little later on. And what that means is a single point location, so where we have two pipes joining, can actually have a node, a pit or an inlet, and a manhole snapped to it. So we can have multiple nodes snapped to that one location. I think that's where a lot of the confusion to do with nodes comes from, is that you may have to have multiple points connected to that one location. And then obviously we've got the 2D overland flow component, which is when we can also do some things with 1D hydrology there as well and apply that to these nodes. So just the two highlighted points there, they are optional. We don't need to include them. TwoFlow has a way of automatically generating your nodes, which we'll talk about later, and also automatically generating the manholes and the associated hydraulic losses that go with that. So this is a simple pipe network. If you've done any of the tutorials, you may recognize it. But all we've done here is brought in a 1D network layer which represents the pipes. And TwoFlow then automatically generates a node at the upstream and downstream end of each of these links, with a naming convention where it will supersede a .1 for the upstream node and a .2 for the downstream node. There are multiple channels connected. It will use the first channel alphabetically. So if you've got a channel called alpha and a channel called beta, the upstream node will be called alpha.1. And for those automatic nodes, the channel storage, the storage associated with the channel length and the channel dimensions is split equally between the upstream and downstream nodes. So each node is then assigned a surface area at different elevations, and it's all calculated based on the length and also the channel slope associated with that link. And then that's distributed between the upstream and downstream nodes. Alternatively, we can then start to add in our own nodes. Like I said previously, this is optional, but you can do this to assign invert levels. So it could be that you don't have invert levels in your pipes, so you can use the node invert levels and interpolate the pipe invert levels from them. Your node invert levels can be different to your pipes. We can assign manually assign storage. So in this instance, when we're assigning it using a 1D network point or a 1D node point, we've got quite simplistic approaches to represent storage. We would just use this length for NAA parameter, and then our storage would be uniform across the height between the bottom of the node and the top of the node. We can also specify a 1D, 2D linkage. So we can specify a type here, and we could set either C, R, W, or Q, and that would allow us to have 1D, 2D linkage at the node as well. Oh, sorry, at the node as well as a pit. As I said, quite simple storage can be assigned using those 1D network and 1D node points. If we want to do something a little more complex, if we want to represent shaft storage, storage chambers, or even floodplain storage, then we can add in what's called a 1D NA node that has an assigned or user assigned elevation versus surface area table. So in this instance, we have two pipes. We might have a node, or we might use the automatically generated node, and then we add on a 1D NA point. That references a CSV file. We reference the elevation column, we reference the surface area column, and that reads in our user-defined storage. And that's quite useful for quite complex manholes, but also storage tanks as well. Manholes. So by default, TwoFlow will define a manhole at all culvert junctions. And a culvert junction is basically where you have two closed pipes connected to each other. There's various different assumptions as to what manhole shape is used, which I'll go on to in a second, and also what manhole energy loss approach is used. But we can also manually override that using a 1D manhole layer. So if there's specific manholes that we want as a different shape or using a different energy loss, that can be done. And we can actually use Tuflow's layering approach to build that up. So we can have automatic manholes. We can then add in some manual manholes. And then it might be that we've got a couple of what if scenarios where we want to try some other manhole options as well. So we can build them up on top of each other. Automatically, Tuflow will generate a manhole at the junction of any closed pipes. In terms of the shape, there's a couple of different options. We can specify the manhole default type. By default, it is set to what we call a CJR. So what that will do is it will set it to a junction if the number of barrels is equal to 1, and there are no parallel culverts, and there is only one incoming outgoing pipe, and the diameter of one circular pipe is greater than 1.8, or the width and height of a rectangular culvert is greater than 1.2 and 1.8 respectively. I should probably point out I'm happy to share these slides afterwards, and all this information is in the manual as well, but I'm happy to share these. If it's not a junction, then it'll be a rectangular based on the criteria there. So if the number of barrels is greater than 1, if there are any parallel culverts, or the diameter is greater than 1.2. Otherwise, it's circular. So that's the default option. So Tuflow will go through, work out the number of barrels that are in each pipe. It will work out the number of parallel culverts. It obviously knows the diameters, and then it will assign the manhole shape accordingly. Alternatively, we could use a CR approach, which is very similar, but we don't have the junction, or we can just say, all manholes are circular, for instance. So we can specify, we automatically generate the manholes, and then we can specify the different types. Got a question?
Yes, can you hear us?
I can hear you, yes.
Okay, perfect. I think it's not quite clear for us the difference between the manhole and the 1D node. I mean, what's the difference between the two, basically?
Yeah, so the way I like to think of it is the manhole is where you specify your energy losses. Okay. So there's no need to have a manhole unless you want to override the default energy loss approach.
Okay. For example, if we have a network with a 90 degrees angle, we want to represent the energy losses for the angle, the 90 degrees. We will use a manhole, right?
You can do. I'll come on to that if that's okay, because the default energy loss approach does account for the change in angle between incoming and outgoing pipe. But if you want to get more specific, so this is the 1D manhole feature, the attributes. So you can change the shape of it. So that would be one reason why you might want to use a manhole. You can change the invert level if you want to. You can change the dimensions if you want to, but probably the main reason for using the manholes is to change the loss approach, and also to change some of the loss coefficients. So there's different ways of changing the invert level, there's different ways of changing the storage. So unless you're really changing the energy loss approach, I wouldn't necessarily use a manhole. Okay. So we have all those. Or the capability to override those within a 1D manhole layer. Like I said, primarily it's to do with the energy losses. So these are energy losses associated with the expansion, contraction of flow as it goes into a manhole chamber, the change in direction of the conduits, as we just talked about, the change in invert level, elevations, and also to account for plunging flow and other things that might exist, some other minor losses. So we have 3 manhole loss options. The first is to essentially switch them off. The second is to apply a fixed energy loss. And the third is the default, which is the Engeland approach, which is quite a sophisticated approach dealing with manholes. So if we specify none, we just use standard entry and exit losses of the connected culvert. So this would be exactly the same approach to inlet and outlet losses. if you had a culvert in an open channel, for instance. So if we specify none, that's what's going on. If we specify fixed in England, then we don't use the inlet and outlet loss approaches. We specify that manhole energy losses or loss approach. So with a fixed energy loss, we just specify a K fixed value, and that is a multiplier of the pipe velocity head for the outcoming pipe. This is the kind of thing that would be based on user specified literature guidelines. It can exceed 1, so particularly if you do have those 90-degree bends, it can get quite high. And this kind of approach is very similar to, I don't know if you've used InfraWorks ICM, but it's very similar to the fixed approach within InfraWorks ICM. The default option is the England approach. So this is what gets switched on automatically. It's a dynamic energy loss that's calculated every time step, and it will represent it will represent the expansion losses between the pipe and the manhole. It will represent the changes in flow direction, so it will work out the incoming angle, outcoming angle based on the digitization. It represents the losses due to the change in elevation between the ingoing and outgoing pipes. We can represent the expansion losses for the outgoing pipe, and then we can add in a manhole exit coefficient, which is user defined. So that's to account for any additional losses that we do need to represent. There are 3 worked examples on our wiki page. So if you do want to get a bit more of an understanding of what goes on for the England approach, they have been written up on our wiki page. And the England approach is very similar to, is also implemented within the Mike Urban and Mouse software. So Bill Syme, who wrote Tuflow, he used to work for DHI at some point, and he incorporated that method into the both software. Another question?
Yes, just a question about manholes. If we don't add manually a manhole, and that there is a manhole that is added automatically, it will use this angled loss approach?
Yes, unless otherwise specified. So you can change the default option, energy loss approach in the TCF, sorry, in the ECF estuary control file. But if you don't, then yes, it will use the England as standard.
So if we put 2 pipes right next to each other, in the middle of the 2 pipes, it will be created a node and a manhole? Both?
Yes,
Okay.
It will. Yeah. So there's I'll show you later. There's one instance where a manhole doesn't get created, but that's usually because of a very distinct mismatch in elevation levels between an incoming and outgoing pipe. But all other times a manhole would be generated.
And if we put manually a node, it will also create automatically a manhole?
Yeah.
And how, if you want to put everything manually, how do you connect each other? Do you put all the points right on top of each other, or?
Yeah, all those points would be snapped together.
Okay.
So we've got the nodes, we've got the manholes, and then we've got the inlets and gullies, or in Tuflow terminology, the pits. And these are what convey the water between the above ground and below ground. As I mentioned, these are input as points, but within Tuflow, they get converted to a channel. So what happens if you view the results, you'll see that they have this little offset line. So what we've done here is our pit is at these point locations on the pipes. But what Tuflow will do is just offset them to basically create this little channel so that you can basically plot the results more easily, and you can just see what's going on. So the connection is on this point, but what it does, Tuflow does, is just makes it easier schematically to see where they are and generates this little channel. That channel by default is 10 meters long. That doesn't account, that's not used hydraulically. That's just for display purposes, and you can change that if you want to. So it gets displayed in the results, but it also gets displayed in the check files as well. Within the 1D network, we can define our pits. And what we can do then is we can specify this connection 1D, 2D, and specify an SX connection. And that means we don't need to digitize an SX option for each pit. We just specify our pit within the 1D network. We would use a type, a Q, C, R, or W type, and then we specify our connection 1D, 2D, and that point then becomes our 1D, 2D connection. We can use the flag L and set it to SXL, and what that does is it allows us to lower the 2D cell elevation by whatever value we put in the upstream invert. So it just gives us a little bit of a sag to make sure we're collecting flow from the surface. And then the number of 1D, 2D connection cells is automatically calculated by 2Flow based on the size of the pit and some other parameters that can be changed. That 1D pit, or the pit specified in the 1D network line, doesn't have to necessarily snap to a node. So we could have, for instance, you could have your manhole and say that's the point where our 1D and 2D connect to each other. But it could be actually, if you think of a street, you have a manhole in the center of your road, and actually your inlets are on the edge of the road along the curbs. So what we can do is we can have our node, we can have our manhole, but then we can have our pits along the side of the road. We can manually connect them, but 2Flow has this quite neat functionality called pit search distance, where it says, well, okay, if I've got a pit within, I think the default's 10 meters, if I have a pit that's not connected within 10 meters of a node, it will automatically connect those. You can also do it manually with an X connector. So if you are modeling, if you've got separated sewers and you might have a stormwater or surface water sewer down the center of your road, you might also have a foul sewer. You don't want to be connecting your inlets to your foul sewer. So if you can override it using manual links as well. In an SX connection, the 2D water surface elevation is applied as a head boundary to the 1D domain. The 1D hydraulics is calculated using the chosen method. So usually with a pit, it's done using a head discharge relationship. So we're taking the water level from the 2D domain. That's given us our head, which is then given us a discharge, which is then applied into our 1D subsurface network. Likewise, on the opposite side of things, we then apply a flow into the 2D domain where we've got flooding out of the 1D subsurface network into the 2D domain. The other type of connection, a HX connection, is taking the water level from the 1D domain and applying it to the 2D domain. That's typically used for where we have open channels. Where we have subsurface pipe networks, it's usually the SX connection that's used. Obviously, that 1D, 2D connection and that interaction between the subsurface and the surface depends on a lot of different parameters and circumstances. So obviously, it depends on the water level in the 2D surface. It depends on the hydraulic head and the capacity within the subsurface network. Depends on localized topography and depends on the inlet gully type, surface flow velocity and direction. And we can get a relatively good idea on most of those, but then we have blockages which completely confuse things and are quite transient in nature, so pretty much unpredictable. So there's a whole host of things that we need to try and account for when we're trying to represent that subsurface surface interaction. I'll come back to that in a second. So we have various different inlet types. The first is to use a culvert routine. So for this, we can specify an R type or a circular type. And what they do, they just calculate the inlet and outlet losses based on the assumption that this is just a rectangular culvert. It's not a great way of doing things. Alternatively, we can use a weir type. So with this, the width is set to approximate weir flow. You probably go back to this one, probably a better example here. So it's assuming that flow just weirs over that crest level. Obviously, we've got a width, which is the width of the inlet, and we just have flow wearing into the subsurface pipe network. This provides quite a poor representation where we've got quite deep flow up against our inlet. Therefore, the approach that I think most people use is to use a Q-type, and this allows you to specify a depth discharge relationship. And that depth, like I've mentioned, comes from the 2D domain, and then the discharge is calculated from that depth and applied to the 1D domain. With this, you need to know a bit or make some assumptions about pit types. And what we do is we set up a database within TwoFlow in the CSV file, usually called a pit inlet database. And it's very similar to the boundary condition database that you might be used to. And we basically have a library of different inlet types. We have a source CSV file, and then we basically say what depth, what columns giving us our depth, and what columns giving us our flow. So we can see here, this is the actual pit inlet curves. We have a depth, and then we have a capture rate for different inlet types. And there's a whole host of documentation of how those depth discharge so that potential depth discharge relationships for a host of different authorities. I don't have one for France, but there's certainly some in the UK that we use. And obviously within Australia, there's a lot of examples as well. And what you tend to find is that the individual manufacturers of these types of equipment have a depth discharge relationship for the particular gully or the inlet. Got a question, Quinton?
Yes, what's the difference between using a pit or a 1D node with a 1D, 2D linkage?
Not a lot, to be honest with you. Can I come back to that one if that's all right?
Okay.
Possibly with a couple of examples towards the end, might be able to just show you the difference. The way I tend to think of it is your node is always at the intersection between two culverts, so it's probably more likely to be a manhole, where your inlet is actually representing the inlets on the side of the curbs.
Okay.
Hopefully, explain that in a bit towards the end. We also have this concept of virtual pipes. So it's quite often difficult to get the information about the full subsurface pipe network. So what the virtual pipes allows you to do is actually to represent the capture rate from those inlets and gullies, take it away from the 2D surface, but actually not to bother with routing that in the subsurface. So we can take flow away, we can drain it away, and then basically say it's lost to the model without having to represent the full subsurface drainage network. Through time, this has become a bit more complex. So there's 4 different modes of operations as such. So the first is what I've just described there, which is to take the flow away from the 2D surface and then just lose it from the model domain. So quite similar in some aspects as to how 2D infiltration works. It infiltrates flow from the surface and then just says, right, that's lost. We don't have to deal with that anymore. The very simplest way of using virtual pipe captures the flow from the 2D domain and then just loses that from the model. The other approach is to take it away from the 2D domain and then apply it elsewhere within the 2D domain. So we might say, we've got all these green dots, which are my virtual pipe inlets. We take flow away from these, and we might say, actually, all of these end up discharging into this river. So we can take all the flow from there and we can apply it into that river. We can do that. And the third option is actually say, we have a capacity as to how much can discharge into that river. We have an outlet capacity. And then what that does is it surcharges back out some of these nodes on virtual pipes. So we can have a limitation on the amount of flow that gets into these inlets. That's our depth discharge relationship. And then we could say, right, it all drains to this location in the river, which is represented in 2D. And then we could have a limitation on the outflow. And then we can backwater up into those systems. The other approach, which is supported by some of the more recent versions of 2Flow, is to say, right, let's take flow out of these, or take flow from the 2D surface at these inlets. We're probably not going to represent the smaller pipes, but we might have a bigger subsurface network, and we might say, right, okay, you know, this pipe, these virtual inlets here, we're going to apply to a pipe down here. So we can actually represent some of the drainage system fully in 1D, and then we can represent some of the more minor drainage system via a series of virtual pipes where we're just accounting for the drainage into the network, but we're not actually doing any routing between where the flow is captured and where we're applying it to. For virtual pipes, we define those within a 1D pit layer. So these are of type VPO or VPI. So if it's a VPI, that's our virtual pipe inlet. That's where we're taking flow from the 2D surface primarily. And then we have a VPO. So if we want to apply it to the 2D domain, we use a VPO, which is a virtual pipe outlet. And that can be connected within the 2D domain, or we can actually connect it to the 1D. And then just like a 1D network layer with a Q type, we can specify the inlet capture curve. We can specify the amount that comes back out of, or the amount that goes back into the 2D domain, that virtual pipe outlet amount. We can then say, okay, if our VPO is surcharged, where does the water go? We can specify a virtual pipe surcharge index. So we might go for certain pipes before others. It's a bit more complex. And we can also apply blockages to pits as well. So if we do have knowledge, or if we want to do some sensitivity, we can set up blockage associated with those. And we can do those with the standard inlets as well. What we can do as well is we can specify different networks. So it could be that this network in yellow, we say, right, these are all my virtual pit inlets, and then maybe this one just here is our virtual pipe outlet. So everything in yellow drains to that one point. Everything in orange is a separate network, and we might just drain to this point here. So we can actually set up different virtual pipe networks within our wider model domain. This just gives an example. So we have a 2D model of a river channel, and we have some virtual pits, virtual pipes, sorry, with the virtual pipe inlets. So there's no representation of the subsurface network here. And what we've got here is just two virtual pipe inlets. And we can see the flow coming through those virtual pipe inlets. We've also got this 1D link down here. And this is just taking flow from the 2D surface, and that's what is coming through this pipe at this point in time. So in this instance, we're just taking flows from the 2D domain and losing that from the 2D model. We're not accounting for that in the 1D network anywhere. In this instance, and it's quite common within the UK, is we say that our inlets can only capture 10 litres per second. So in this instance, we can see this cap in our head discharge relationship to stop too much flow being captured by those inlets. We might have the situation where we're applying it to the 2D domain. So we could say everything in this location is being drained to this point. So we have a virtual pipe outlet, and that's what we've got here. Negative flow is flow from the virtual 1D domain to the 2D domain. So we're draining flow at all these nodes, and we're just applying it to that 2D location. We can also, so in this instance, this is uncapped. And as I mentioned, we can cap that. So in this instance, we've just capped it to 1 cubic meters per second. So that's the amount that can surcharge from that outfall. And then that has an impact. So if we just go through, we can see the inlet capture. And if we start to cap that, obviously that has an impact on the amount that can be captured by certain inlets. And that's all based on the virtual pipe surcharge index. I think by default, what it will do is it will do it on elevation. So if you haven't specified a surcharge index, i.e. the order that the virtual pipe inlets will be limited, then it will just base that on elevation. We can also apply it to the 1D link. So in this case, we're not applying it to a 2D output. We're saying, right, let's apply it to here. So we can see this is when I'm applying it to the 2D domain, but I can actually apply it to the 1D domain if we wanted to. So not applying it here, we're applying all the flow and just saying, let's apply that to this location. Until the very latest release of 2Flow, which was released formally this morning, the transfer of flow from the virtual pipe inlet to the virtual pipe outlet was instantaneous. But what we've added in the latest version of 2Flow is you can represent a lag or a shift. So you can actually apply a shift and some temporal, just a lag between the capture of the flow and where it comes out at the outlet. So that's the virtual pipe, virtual pipe functionality as well. I'll just very quickly talk about the outputs. So obviously you're adding in a number of different nodes and a series of different lines. Always use the check files. So there's the node check file. This will give you the various elevations associated with it. It will tell you that a manhole's been automatically generated. It'll give you any additional storage. The manhole check file will tell you what loss approach is being used, what the invert level is. It'll give you any parameters that have been assigned to it. So if you want to set up just a pure pipe network without any nodes and you want to just double check that manholes have been generated, then this manhole check file is really useful. In terms of the inlets and gullies, we've got this pit check file, which again gives us information, what type is that pit set to, what inlet type is being used, the invert levels. And if you want to double check the 1D, 2D connectivity, then the 1D, 2D check file is the one to use. Really useful, particularly with the way 2Flow layers up the input layers and the lower layers supersede those ones above. You want to use the check files to just make sure that 2Flow is seeing the domain and the network in the way that you wanted it to. It's also worthwhile, these check files are created at that pre-processing stage before the actual simulation. So if you're running a simulation for the weekend, have a quick check of the check files before you go away for the weekend. Nothing worse than coming in on a Monday morning and realizing your results are all wrong because you made a simple mistake. So make sure you use those check files. In terms of manholes and energy losses, these can be viewed. So there is this time series loss file, an _TSL_P, excuse me, which is output for each channel. Gives us the flow regime. Excuse me, my voice is going. So this gives us the flow regime, which is shown by a letter. So A is empty, and then D, E, F are slightly different flow regimes. It's all described in the manual. And then it gives us 3 values, which are our entry losses, form loss, and exit loss. So we've talked about entry outlet losses a little bit. We can also add in bend losses if needs be, or other minor losses. So we have this CSV file, this shape file or geopackage if you're using geopackages file that gets generated, and essentially each of these is a different time step. That's been superseded a little bit by the fact that we can now view these within the 2Flow viewer. So we can pick our link and we can see the entry losses, the exit losses, and the additional losses within that. So we can just plot up the losses. We can also plot up the flow regimes as well. So we've got full sight of what's going on for each pipe and how that changes in with time during the simulation. We can plot the captured flow. So when we bring in the 1D results, like I said, we have these pit offsets, and we could select those and see how much flow is coming into the individual pits or you can take a selection of those and plot them all at once. And then really usefully, we can see pipe networks within the long sections of the pipe networks. So we can see in this instance, we've got the pipes represented in gray. The blue is the bed level. So this actually drains into a river channel, and then we've got a weir at the downstream end. We can plot the time varying water levels, but what we can also show is the pit ground levels as well. So we can quite quickly see which of those pits should be inundated or discharging, flooding, essentially, and we can start to identify those using that long profile. And it's this, until relatively recently, and probably the last couple of years, we've not been able to see within TwoFlow, so it's probably made TwoFlow quite difficult to use from a pipe network functionality point of view. But with this capability, it really opens up a lot of possibilities. There's a question there.
How do you define the beginning and the end of your long profile? Do you have to select each pipes?
No, so there's two ways of doing it. You can just select one location at the upstream end, and it will just basically do it based on continuity. Or you can select an upstream and a downstream pipe, and it should generate the pipe in between it. Alternatively, there is a third option, actually, which is there's a pipe integrity tool. And what you can do with that is select a downstream point, and it will give you all the upstream, what's the term? So it'll give you all the upstream traces that you can use, and you can actually save those out as individual long sections, and then you basically just go through them one by one to double check the results. There's a really useful tool within the pipe integrity tool.
Okay, and in this representation, the riverbed is in 1D?
Yes.
Or it's, okay.
Yes.
Okay.
Yeah. So that's the outputs. I just wanted to work through a little example with you to, hopefully clarify some of the things that I've been saying in terms of having multiple lines and nodes and manhole layers and things like that. So this is, that very simple model. And what we've done here is I've just read in a GIS 1D network pipes layer. So there's no nodes defined here, no manholes or anything else. And what we can see from the check files is nodes get generated automatically and manholes get generated automatically. So we can see here, might just be able to make out, we haven't got an upstream and downstream closed pipe at this location, so we don't have a manhole there. May or may not be a problem. Might need to add in a manhole at that location. Likewise, here we haven't got a downstream pipe, so there's no manhole generated at that point. But just using a simple pipe, we have automatic nodes and automatic manholes generated. And we can see the manholes here, they're all set as type circular. They use the England loss approach. They're taking the invert level from the pipes, and there's a whole host of parameters there associated with them as well. This is just another quick example. So this is what I was saying earlier about, automatic manholes get generated pretty much everywhere. We can see that. So the green dots are all our nodes. The white dots are where manholes get generated. We don't generate a manhole here because there's no upstream closed pipe. In this location, we have two upstream closed pipes, but no downstream pipes. So no manhole gets generated there. And then there's
connection.
Sorry.
Sorry, excuse me. Sorry. Now we just sorry. We just had a question. Is the automatic manhole option is by default?
Yes. Yeah.
Okay. Okay.
So you can turn that off as well if needs be.
Okay. Thank you.
And there's also another location here where one doesn't. So in this case, we do have an upstream. We do have a downstream closed pipe, but no manhole's been generated. And the reason being is we've got a drop here, such that the invert level of one pipe coming in is much higher than the soffit level of the pipe going out. So at that location, it's probably not appropriate to use standard manhole loss approaches. And to be honest with you, that's probably in this case indicates a problem with the input data more than anything. So, you know, that kind of drop would be probably better represented using a WEA. So that's one location where manholes don't necessarily, or probably won't be automatically generated. We can add in manual nodes. So there's a couple of reasons you might want to do that. So these are the nodes that get generated automatically. The name is based on the pipe. So in this instance, I've just called them pipe 1, 2, 3, 4, 5, etc., etc. However, in this instance, I'm just using a definition of nodes just to change the name of the nodes, just to make it easier for me to work out what's going on. I can also use those nodes to specify a 1D, 2D connection. So you'll see I've used my 1D network node layer. They all have a type of queue. We have an inlet type and a 1D, 2D connection. And as a result, at each of those nodes, each of those manhole locations, we now have 1D, 2D connectivity. Any question?
Yes. The nodes that you generated automatically, they don't have a 1D, 2D connection by default?
Not by default, no. So the automatic nodes don't have 1D, 2D connections.
Okay.
So that's,
and there is, sorry. There is no line on the code that we can use so that they are connected.
I will have to check that one for you. I'll get back to you on that one. I don't know off the top of my head. That would be, you know, that would be the normal reason or the usual reason of why you'd want to use a 1D network layer for the points, is to specify that 1D, 2D connectivity. But I will get back to you on that one because that is something I have been meaning to check myself for a while as well.
Okay, thank you.
It could be something that we stick into the software as well if it doesn't exist. So yeah, so now, you know, we've used the pipes, we've used the nodes, so we've used the nodes to change the name, and we've also used the nodes to create a 1D, 2D connection. Another reason we might want to use nodes is if our, you know, if we've got a point data set of invert levels and our lines don't have upstream and downstream invert levels in them, we can use -999, and wherever we use -999, that's going to do an interpolation. So in this case, we're going to be taking, we've got -999 in our node layer, so it's going to be taking the downstream invert from our pipes, and it's going to be taking the upstream invert from our DTM. However, our pipes can have upstream downstream invert levels of -9999, in which case they will look for defined elevation within the nodes. In this instance, we've then got two nodes where we have defined storage. So these might be storage tanks. So we've just got two nodes. They snap to the existing manually defined nodes. These are what we call table links. So we read in the 1D NA and there's a shapefile, specify a CSV file. We have a column with elevation, column of area, and then this defines the storage at that node location. So it's not automatically generated storage, it's manually defined storage. And we can see here, this is what we have if we have the usual approach. You know, our bed level is based on the upstream downstream invert level. Well, actually now, you know, we've added in our storage tank, the bed level is at 40.5 rather than 40.99. So we're overriding that value. Whichever one comes further down the list in our ECF takes precedence. And then also we can see that now we've got this storage array, which matches what we defined, although, you know, there's a slight difference in the surface area just because of the way 2Flow also accounts for the pipe as well. So we've got our pipes. They're generating most of the manholes, most of the nodes. We're overriding some of the nodes in terms of providing that 1D, 2D connectivity and also the change of names. We've got a couple of locations where we're changing the storage. So we're having manually defined storage. We've then got two locations where we're defining manholes. These manholes are defined. We're using a rectangular type, and we're changing the loss approach from the default England approach to a fixed approach. And then I think I might have changed a couple of other parameters as well. So this is the check file. You see everything's been set to England, apart from those 2 manholes that I've defined. And what we can do is plot up the results, and you can see there's a difference between particularly the exit loss coefficients between the England and the fixed approach. So in this instance, we've just added in a 1D manhole layer just to change the energy loss approach that we're using at those manholes. So it could be that we've got a bit more additional information. We might have some flow data or velocity data upstream and downstream. We've got to do a bit of calibration, and we've worked out actually, you know, in these locations, a fixed approach is better than an England approach. In this instance, we've then got virtual pipes. So we've got some virtual pit inlets. So we've got our pipe network down the center of the road. We've got our 1D, 2D connectivity at the center of the road, and then we've got our inlets at the edge of the road. Sorry, Brenton, you got a question?
Yes, sorry, before you begin another example about the storage. Let's say we want to represent the flooding from a storage to 2D domain. So I assume we could put 1D, 2D connection, like a C 1D, 2D connection, if the flooding is only from a circular manhole, like a manhole on the storage. How do you define the dimension of the flooding exit from the storage? I don't know if it's clear. My storage can flood on the 2D domain, but only by a hole, a circular hole, let's say 1 meter diameter.
Yeah.
How can you define that?
Pass. Let me get back to you on that one as well. Sorry. There are ways of doing it. I'm pretty sure, but I'll just double check for just define storage node. Define 1D storage node. So essentially, it's the essentially it's the number of nodes that it interacts with, number of 2D cells that it interacts with.
Yeah, just we try to represent the flooding from storage,
Underground storage. Yeah.
underground storage. I assume we can do it with pips, with pipes, probably.
Yeah.
But if we want to do it
Right on top.
from
Or
the
automatic.
storage object, how is it working? I mean, how to flow calculate the flooding from the storage in surface?
Yeah, I'll get back to you on that one.
Okay.
I think there's, just bear with me a second. I think you'd be able to do it because your storage is, so your 1D NA is just being, it's just defining the storage. You'd also have a node there, and your node is defining the 1D 2D connection, and then this connection number, I'm pretty sure that controls it. I'll get back to you on the specifics on that one,
Okay.
but it's that connection number which gets applied. I'll write some text and send that across.
Yeah,
just to confirm that one.
Thank you. And just link to this question for the storage, when you define the depth surface tables, do you have to put like at the top of the storage like a Pressman
Priestman start. No, you
to
won't.
represent the over
Yeah. How do you represent the top of the
Yeah,
underground?
so
Sorry.
TwoFlow has this. I'm just going to dig up the manual. It has what's known as storage over obvert, which is automatically, so it's like an automatic Priestman slot to a certain degree. It's a slightly different concept, but it's adding in some storage above the obvert, and it tapers that as well. It's pretty small, but it's a very similar concept to a Priestman slot.
And how do you define the top of your underground storage system? Is the last line where you put the storage versus the area versus height?
What I would do is always set a value of 0 at one just above
okay.
The highest point, just like put a lid on it essentially. So in this instance, manholes we've covered. So virtual pits. So we've got the virtual pits along the edge of this road in this instance. This just provides us with the 1D 2D connection again. So in this instance, you'll note that I haven't got the manholes represented. I've just got the inlets. They're providing the flow. So this is, I'm just using the GIS pit layer here, the virtual pipes. So this is taking the flow away from the 2D surface, but we're not actually applying it to the 1D pipe. So you can see here, this is the flow captured through this virtual pit inlet. This is the blue line is the flow through the pipe, and we can see that's 0. What we can do is use the pit layer in conjunction with my pipe network. I've got this pit search distance of 30 meters. I think the default's 10. And what that means is these virtual pit inlets, these inlets now, pits, because they're just a Q type, although they're not snapped to those nodes, TwoFlow will go away and say, right, okay, that's within my search distance of that node. We're going to automatically connect any flow that comes in through this point to the 1D subsurface network. Any flow that gets captured over here gets applied to the nearest nearest node. So we're using virtual pipe, we're using the pits, but we're using them with the full representation of the subsurface network. In this example, we were just using the pits, but these were virtual pits. They were just taking flow away from the model domain, and they weren't actually doing anything with them. So Q-type pits, we're using a defined AB type. That's defining our depth discharge relationship. And you can see if you bring in the 1D network file, what it will show you is it will show you the pipe network, it will show you the pits, the inlets, and then it will just show us the automated connection that pit search distance is generating. Like I said, we can manually add in that connection, so we could specify an X connector between our pit and the node that gets generated if we wanted to. So like I said, when you do have foul sewers and storm sewers, that is quite often needed. There's various tools within QGIS that can be used to help automate that.
Just a question. With the bits that you don't link to pipes, if the detection is lower than the actual length, is the pit converted to virtual pits automatically?
That's a good question. No, I don't think it is. So we've got, TwoFlow, sometimes things are a bit too complicated, and this is possibly one area where it is. So with the case of a Q-type pit, that's just an inlet. So that is looking to connect to a 1D pipe network. So that will give an error. We can set up virtual pits to connect to a VPO and assign that to the 1D, which works in a similar kind of way. So that will just connect it regardless of the pit search distance. So I would kind of try and keep things simple and just use the Q-type pits if you're wanting to connect to the 1D domain, because then that will give an error if it's not within that pit search distance.
Okay, thank you.
Just a question about nodes. What's the main difference between 1D network points and 1D node points, ND and NWK?
There's no difference into what they actually are. The only difference is in the actual GIS tables, in that the 1D node is slightly I think it's a bit more simplistic. So there's a few more assumptions in terms of the actual parameters that you have to put in, but fundamentally they are the same.
Okay.
It's the same with a 1D network point layer and a 1D pit network. You can define the same in both, but the 1D pit is slightly more simplistic attribute table, so there's less information that has to be added. So yeah, so we have that automatic connection, and in this case we've got the capture from that inlet, and this time if we plot the flow through that pipe, we've actually we've got that flow being brought in, and it's actually added to the flow that's within that pipe already. So the flow in the pipe is obviously greater than the captured flow because there's more capturing further upstream. Like I said, in the latest release that was announced this morning, we can now apply a shift or a lag to that captured flow from the inlet to the subsurface pipe network. So, we can do, hopefully, this is my summary of what I've just covered here. We can read in the pipe layer. That gives us, the shape of the pipe, the invert levels, the lengths, various other things. We can read in the nodes if we want to. We can change the node names. We can change the invert levels. We can change the node. We can connect to the 1D, 2D. We can read in a GIS manhole layer. That gives us the energy losses, and we can change those. We can bring in 1DNA table links. That allows us to define storage tanks. We can then bring in virtual pipe inlets or virtual pipe outlets as well. And then we can have those pits give us those inlets, that pit search distance to help us define where we're taking flow from the 2D domain and applying it to the 1D domain. Fundamentally, to have a 1D, 2D connected pipe network, all you need is the pipe layer and the pit layer. However, each of the other ones is optional. So if you want a bit more control over the nodes, you can add in a 1D network or a 1D node layer. If you want more control over the manholes, you can have a manual 1D manhole layer. Remember, just with the pipes, nodes and manholes are automatically generated. So we're just overriding those automatically generated nodes and manholes. We can have optional storage definition. And then if we want virtual pipes, we can add in those as well. So we could add in just pipes and pits, and we could have that 1D, 2D model. But if we want to add in more detail, we can do that with the various different options that we have available to us. Host of resources, which I'm sure you're familiar with. Like I said, I'm very happy to share this presentation with you, and I'll get back to you on those couple of queries as well. But happy to open it up to any further questions.
Maybe not a question, but thank you. Thank you so much for all the explanation. I think it's not very easy to understand the difference between 1D pit, 1D network. It's the same with not the same parameters. One is more complete than the other, etc. So we have to process all the information and to synthesize everything. But now it's more clear. I think it's clear. It's clear, and maybe we have some little question, very technique, and you will come back later with some answer. Mostly concerning the flooding, the flooding from subsurface network to the model, when it's not only a pipe, but from a storage or from a manhole. It's not still quite clear if we could just use a 1D, 2D exchange with a C type or R type. Is it enough, for instance, for
what I would probably use the depth discharge, the Q type, and use the depth discharge curve. The one thing I did jump over very quickly, and I said I'd get back to, was so at the moment, where you specify a depth discharge relationship or a C type or an R type or W type, it's not possible to have different approaches for the inflow. So there's a drainage of flow from the 2D into the 1D, and then the flooding from 1D to the 2D. They kind of have the same depth discharge relationship, for instance.
Okay.
It's not possible to have separate ones of those, but that is on the development list. So yeah, I would use the Q type myself and use a depth discharge curve, but I appreciate that in some instances, that's not always possible. Likewise, I don't tend to have the manholes connected to the or the nodes connecting to the 1D, 2D. This because in most instances, a manhole's not what floods. I know you do get popped manholes, but it's the inlets which are the main mechanisms for connectivity between the surface and subsurface. Yeah, I do appreciate you do get popped manholes every now and then, but it's pretty rare. I've seen some very high pressure and do their best not to pop.
Yeah. But you don't advise the C and or air type because it's too simplest to.
Yeah, I see. Yeah, I've never used the CRR type. I have used the W type purely because that's kind of the default approach in InfraWorks, which is the background I come from. So the 2D flood type in InfraWorks is based on the weir connection. So that's the most simplistic way of doing it. If you're modeling a whole city, you don't have information about every single inlet. So if you need to make a gross assumption, that's one of the things that gets done. But I know certainly the Q would be recommended by us where you have that data available. Certainly in the UK, we've started getting that gully information openly available as open data. Alternatively, quite a few of our scientists get out on site or use Google Street View. You quite often see them in the office driving down the streets on Google Street View, trying to work out what the inlet types are so that we can apply those.
Okay. Thank you. And maybe one other question. In terms of performance, if we use virtual pipes on a big area, big territory, to modelize the absorption by the network without modelize it completely, is there a risk of instabilities, a slower calculation because of a lot of virtual pipes, or is it stable?
It's pretty stable because at the end of the day, it's just a source term taking flow away from the 2D surface. Obviously, you've got that additional calculation of calculating the amount of flow that gets taken away from the 2D domain. So it does add a few more calculations from that respect, but you'd be representing the drainage, so you'd have fewer wet cells. So you'd speed up your simulation from that perspective. And it's also a bit quicker. Well, it can be significantly quicker than representing the full subsurface pipe network, particularly where you've got large networks and you're running on a GPU card. There's been a few situations where we've seen models where the 1D really does start to constrain the simulation speed.
Okay, but basically there is no great risk of instabilities using this representation.
No.
Okay. Thank you very much. Vous n'avez pas d'autres questions?
Non, franchement, c'était.
Okay. Again, thank you very much. It's very we really appreciate this kind of webinar. It's very clear, and it's very useful for us to use this 1D elements into Flow. So, thank you.
Great, not a problem. And I think Arno, you've got a couple more topics to potentially go over. But if there's anything else, just give us a shout and we can see what we can pull together. Yes. Really want to support you guys using the software.
Okay. So you just released a new version, right? Last week or?
Yeah, so there's the 2023-03 AB. So the 2023-03 AA was released back in March. And then this latest one, it's kind of like a patch release. It's a minor release.
Okay.
But
We'll look at the improvements in this release. Okay.
So one of the ones, like I mentioned, is the ability to add in a shift and a lag to the virtual pipes.
Yeah.
Add to that functionality.
Sur les VHR qui ont disparu quand on.
Ah oui.
C'est quoi ça?
Sortir raster, mais ça c'était, je sais pas si.
Ah oui, non, mais ça on en aura peut-être un. Ok. Thank you.
Okay.
So it's okay for us, Arnaud. I don't know if you.
Can't hear you, Arnaud. I think you might be on mute.
Yeah, Arnaud is writing something in the
conversation.
In the text, in the conversation, in the chat. He has a question for you. En fait, ce qui est super intéressant, je trouve, c'est que il crée en virtuel automatiquement tout ce.
The suspense is killing me. It'll be a very good question.
Ah oui.
Ah yeah, okay,
Yeah.
Arnaud. Wait, maybe I can, I can explain you. In the last release, the Hey from March, we no longer have the HR velocity results.
Okay.
It produces the height, HR,
Height.
but no longer the
Yes.
V, the velocity HR.
HR.
Okay. Bear with me 2 seconds. I'm just going to talk to my colleague who's responsible for this, who's sitting opposite me.
Okay. Thank you.
HR float velocity results didn't get
Yeah.
created in 2023.
Velocities don't have.
All right. Anymore.
They were in beta.
Sorry.
They were in like one of the beta versions, but in 2023 they were disabled because we can't answer it.
Okay. Cool. Super. Thank you. So apparently they were available in the beta, but they were switched off for the release because just for the high resolution results, because it didn't really make sense to do the interpolation onto the high resolution grids. So they were switched off purposefully.
Okay, it's switched off. Okay.
And just another question. I saw that we can have one result of the model that is velocity against high cross, according to a table. Can we do our own table, or can we only use those that are already pre-processed?
You can only use those ones that are pre-processed, but if there is one that you guys want to use, then if you want to send us across a description, we could look to implement that one.
Okay, we will see, because it's a variable according to our clients, so we don't have one table, one reference table for all friends clients, but okay, it's good to know.
Yeah.
Thank you.
Yeah, if you want to feed that, we can.
It's a variable. Yeah, exactly. But for the V, for the HRV, we agree it's not. There is no sense, no physical sense.
Yeah.
It was just convenient for us to get the same grid at the same extent for height and velocity, but to represent the results. But it's not. We agree. It's not. It was convenient. More for mapping consideration, but for physical there is no sense. We agree, but just it was convenient. Yeah. To get okay.
That's useful to know, because we might be able to do something without the interpolation